Here are some examples of several liquids. We do not have to memorize things from this table, although we generally do want to know some properties of water. So we have examples. Water. Water has hydrogen bonding. It can form a couple hydrogen bonds on each oxygen. And it has two hydrogens on each oxygen for forming hydrogen bonds with other oxygen. So it has a strong capability for forming hydrogen bonding. Isopropyl alcohol can do hydrogen bonding on the alcohol group, but the 3-carbon group for the propyl weakens the hydrogen bonding. So we have hydrogen bonding, but it's been weakened a little bit with the presence of the hydrocarbon group. Acetone is also 3-carbon, but it has a carbon double bond oxygen, no hydrogen bonding, but it will have a dipole-dipole interaction, which would be a pretty significant dipole-dipole interaction. Diethyl ether has oxygen between two carbons. This will give it a dipole, but it's going to be a weak dipole-dipole interaction. Then methane is just a pure dispersion forces. So the weakest intermolecular forces down at the bottom, and as we go up toward the top, we have stronger intermolecular forces. And we see that our melting point just increases as you go from weak intermolecular forces to strong intermolecular forces. We have the same thing with our normal boiling point. Normal boiling point increases as we increase our intermolecular forces. Now, it's not quite as perfect with heat of fusion or heat of vaporization. Heat of fusion here is not a linear. We have a spike with the diethyl ether having the higher heat of fusion. But the general trend is that the weaker intermolecular force will have a weaker, smaller heat of fusion, and the stronger intermolecular force will have a higher heat of fusion. And heat of vaporization is similar. It's not perfect between the two hydrogen bondings up here, but generally the weaker intermolecular force will have a smaller heat of vaporization, and the stronger intermolecular force will have a larger heat of vaporization. When we take a material, a solid, and we heat it, first thing that the solid does as we heat it is it gets warmer. So as we heat a solid, it'll just get warmer until it starts to melt. When it starts to melt, and we have two physical states, solid and liquid, then the temperature will stabilize at the temperature called the melting point. And it'll stay at this temperature while we have the two physical states. After we have melted all the solid, then the liquid will start to increase in temperature. And liquid will keep increasing in temperature as we continue to heat it until it starts to vaporize or boil. When it starts to boil, the temperature again stabilizes at the temperature of the boiling point. And it'll stay at that temperature until we have boiled away all of the liquid and have left with only the gas. And if we have the gas in a contained system and we keep heating it, then the temperature of the gas is going to increase also. There is a interesting aspect of liquids and solids. If we have a container containing a liquid with liquids and vapors, if we can have a sealed container with a liquid and its vapor, and we heat it up, as we heat it up, more of the liquid will vaporize, making the density of the gas higher. The density of the liquid will slowly decrease until we hit a point where the density of the gas and the liquid become equal. And then the line between the liquid and the gas disappears. So when we hit a temperature pressure where that liquid and the gas just disappear, the distinction between liquid and gas just disappears, called the critical point. and that will be the critical temperature at which this distinction between liquid and gas disappears, and the critical pressure at which this distinction between liquid and gas disappear. If we continue to heat it or increase the pressure, we enter the realm of what's called a supercritical fluid. It has properties that are different from liquids and gases, properties that are affected primarily by the density of the liquid, of the fluid, and we can modify those properties with additives. And we use supercritical fluids for extraction of caffeine from coffee beans, or for dry cleaning clothing. And this is the transition I was talking about. So if we have the fixed container, as we increase temperature, pressure is going to increase. We're following the equilibrium vapor pressure line between liquid and gas, but the gas will increase in density and quantity as the liquid decreases in quantity and decreases in density, until finally they end up at the same density, and the visible line between liquid and gas disappears. We can no longer see a difference between liquid and gas. Now we have a variety of materials that behave in different fashions, solids, liquids, and gases at room temperature, some that can only go from solid to gas at room temperature. So we can show the variety of properties of these materials using what are called phase diagrams. So a phase diagram is going to show the physical states of a material as a function of temperature and pressure. And we're going to learn how to read these phase diagrams. On phase diagrams, we can have triple points. Triple points is whenever we have a set of temperature and pressures where three states of matter can coexist at equilibrium. So this is one of the phase diagrams of water. We can have different phase diagrams based on the temperature-pressure range that we're looking at. So we're having pressure on the vertical axis, temperature on the horizontal axis. So as we increase temperature, we're moving toward the right. So as we move to the right, we're going to expect that we're going to go from solid to liquid to gas. So if we draw a line, horizontal line, and it crosses three physical states, we know that gas is going to be on the right at the highest temperature, solid is going to be on the left at the lowest temperature. As we increase pressure, what we're going to be doing is going toward the more dense physical state. So for here, we can go from gas to solid. So solid is more dense than gas. Over here, we can go from gas to liquid. Liquid is more dense than gas. Over here, we can go from solid to liquid. This is telling us that for water, under these temperature-pressure ranges, the liquid is more dense than the solid. Well, we know that because we know that ice floats on water. But we also see that by the slope of the line between the solid and the liquid. So having a negative slope here means that as we increase pressure, we're going to go from solid into liquid, which means that liquid is going to be more dense than solid. So water is more dense than ice. The triple point is a point down here where you have solid, liquid, and gas all meeting together. So at that temperature and pressure of the critical point, we can have ice, water, and vapor all in equilibrium with each other. If we follow the liquid-gas line up, we'll hit the critical point. This graph ends at the critical point, so normally if the graph continues, that line will end at the critical point. So where the line between liquid and gas stops, that is the critical point for that substance. For carbon dioxide gas, for carbon dioxide. Our triple point is at 5.11 atmospheres, minus 56.4 Celsius. Well, at 1 atmosphere, we have a horizontal line at 1 atmosphere, and there's no liquid in there. So we can have solid or we can have gas, but we cannot have liquid carbon dioxide at 1 atmosphere. It just will not exist. So to get liquid carbon dioxide, we have to have a pressure of greater than 5.11 atmospheres. The line between liquid and gas ends up here at 73 atmospheres and 31 degrees Celsius, 31.1 degrees Celsius. So to get into the supercritical fluid range, which has interesting solvent properties that we can use, we have to be above 73 atmospheres and above 31 degrees Celsius. If we look at the line between solid and liquid, it has a positive slope. That means that if we're near that line on the liquid side and we increase pressure, we're going to go from liquid to solid. That means that the solid is more dense than the liquid. So when we have a mixture of solid and liquid carbon dioxide, the liquid will be on top and the solid will be on bottom. So a heating curve would represent one pressure going horizontal across a phase diagram. So doing carbon dioxide here, maybe about 10 atmospheres. So we have the ability to have solid, liquid, and gas together. If we start off with solid, we're going to warm up the solid. So we're going to warm up the solid. When we hit this line, the temperature will stop, and we're going to stay at this line until we have converted all the solid carbon dioxide into liquid carbon dioxide. Once we have converted all solid into liquid, now we're going to continue our journey across the liquid, warming the liquid up until we hit the vapor pressure of the liquid. So that temperature will be the local boiling point at that pressure. And we're going to stop at this point at that temperature and until we have vaporized all of our liquid. After we have vaporized all of our liquid, then we can raise the temperature of the gas to higher temperatures.